Dear friends, let us begin today's webinar by Atul Bhat, Professor Atul Bhat from Purna Prajna College, Udupi. I welcome you all to this webinar series. This is the third day of our webinar series conducted by Department of Physics and Philomena College in association with Pilikula Regional Science Center. Yesterday, we had an excellent webinar by Professor A.P. Bhat, who spoke on Bhumi Bugari Tirugata regarding the wobbling of the earth and how the seasonal variation happens. And today's webinar is now entirely on the different topic, whether there is a presence of Earth-like structure outside the solar system. And probably there may be a star at the convenient distance. There may be a planet like Earth, and it has the weather system, and there is a possibility of the existence of the life. And who knows, there may be a webinar is now maybe going on in that particular unknown in part of the universe. All that exciting topic will be touched by Atul Bhat. I want to introduce today's speaker, the young, energetic, dynamic professor in the Department of Physics of Purna Prajna College. He did his MSc in physics from Jain University. Actually, he did his BSc from Gangadhara College, Mangalore, and then MSc from Jain University. And after that, he worked at Govindas College, Surathkal for 3 years. And from 2019 onwards, he is in Purna Prajna College, Udupi, as an assistant professor in the Department of Physics. And he's a coordinator of Purna Prajna Amateur Astronomy Club, PAC, and which is doing the human work in the field of popularizing the science and the various astronomical workshop and so on. And is presently the coordinator of this PAC and presented paper in the national and international conference, and also been published papers in the peer-reviewed journal. He is well known in the field of coastal area. The Bhat Dvaya, one is Professor A.P. Bhat, and now is this Atul Bhat. Over to Atul Bhat, and so you will begin the webinar. Thank you.
Thank you, sir. Let me just switch on the slideshow. Yeah, I hope the presentation is visible.
1 minute. Yes.
Okay. Good afternoon, everyone. Thank you, sir. Thank you, sir, for the wonderful introduction. It was more than what I have actually achieved, I guess. Anyways, today's topic that I have chosen is about exoplanets and life outside the solar system. I have modified the title a little to say that life that is extraterrestrial, and are there really aliens? And it should be a point of view of physics that we discuss here today. I have chosen this topic because every time we talk about astronomy, every time I conduct a sky watch, every time I go out for an awareness campaign, or every time I have an interaction with the press, more often than not, I get this question where people ask me, are there aliens? Do you think there is aliens, and whatnot? So I don't know if there are aliens or not, but what has physics found out, what have our efforts found out till date is what I'm going to discuss today. So this topic, we will discuss about the various, how we have discovered exoplanets and what we have discovered so far. So human curiosity has been talking about aliens for almost a century now. We have been wondering about life outside Earth for almost, I guess, millennia. But then today, when we talk about our discovery, we have got basically in 1902, I can show you a clipping from a movie here, which is basically a trip to the moon. So in this movie, we can see that there's a small interaction between humans who go on to moon, because back then we had not been set on foot on moon. So in 1902, humans had imagined that there'll be alien life form on the moon as well. So back in the background, you can see Earth is there and so on and so forth. So human imagination has always asked this question, and this has reflected in media in the form of movies. Some of the popular ones are Extra-Terrestrial, E.T., Space Odyssey 2001, the Alien series. We've also got Star Wars, which is entirely based on alien life. Star Trek. We've got comics that talk about Superman, who has come from a different planet. And then latest movies for the younger audience here, we've got Guardians of Galaxy, Avengers, and so on and so forth. We've also got a Indian version of E.T. here, which has been made about a decade ago, which was Koi Mil Gaya, in which we have a human interaction with aliens as well. So thinking of all these imaginations, all this capable combination of alien life, what have we really found out so far? How different are we from the movies? So speaking about the history of discovery of alien life, or if there is any, in 1899, Nikola Tesla detected some radio signals from outer space, but he could not make sense out of these signals. It was just noise, probably. In 1900s, Marconi detected radio signals from outer space, but then people believed it was the signal between Europe and America that he actually detected. In 1924, National Radio Silence Day was observed in USA, where for 3 days, every day for these 3 days, they switched off all radio signals across the continent for 3 hours, and then nothing was observed. Project Ozma was also created by Frank Drake in 1960. Nothing was found. And 1918 onwards, we had NASA searching for intelligent life outside our solar system, and SETI was also found, search for extraterrestrial intelligence. So are we really alone? Given that not much has been discovered, are we really alone? That's the question we need to ask. So here we know that the observable universe today is about 90 billion light years in diameter. So once we know that the universe is so vast, we have also found out that there's about 100 billion galaxies that we've discovered so far. Among all of these galaxies, we have discovered about 1 trillion stars. So among all these stars that we have studied, we have realized that there's about 20 billion sun-like stars in our galaxy. So in spite of such large number of stars, the question that we always ask is, if sun can have 8 planets, of which one can sustain life, how many planets that contain life may exist in our galaxy, in this universe, given that the number of stars, number of galaxies so large? So this brings us to the question first asked by Enrico Fermi. First asked would be a wrong term to use here, but this is the most scientific question that has been discussed about alien life so far. So this is known as the Fermi paradox, where Enrico Fermi, along with Edward Teller and his colleagues at the Los Alamos laboratories, asked them, where are they? Because alien life is not found anywhere in the solar system. We don't find any artifacts. We don't see any evidence of alien life in our solar system. We don't see any signs of intelligent life that comes from anywhere else in the universe, in the form of signals, in the form of any kind of interaction. But I just told you about the stats. There's so many stars and planets discovered by us, and yet there is no sign of life. So where are they? That is a question discussed by Enrico Fermi. And before we discuss the paradox, we need to understand something called the Drake's equation. This is the one and only equation that talks about alien life directly. So the Drake's equation talks about several terms here, where on the left hand side we've got n, which talks about the number of technologically advanced civilizations in our own galaxy. Giving this number is R star, which is the rate of formation of stars in the galaxy. We've got Fp, which is the fraction of those stars with planetary systems, like the sun, which has planets. There's Ne, which is the number of planets per solar system. Like in case of sun, there's 8 with sustainable environment life. So for sun, it's 1 right now. And we've also got Fl, which is fraction of those planets where organic life can exist, because the life may not be organic in some cases. We've got Fc, which is the fraction of civilizations where they've reached a technological state where a signal that can be detected by us may be dispatched by them. Because if a life is still in its primitive form, then it cannot talk to us. We cannot detect them from it. And then we've got the term Fl. I've made a mistake there. It's Fl, which talks about the inhabitable planets whereon intelligent life actually appears. So among all of these terms, this is basically the probability of finding these are all the terms that give us the probability, and we are multiplying all these terms to give us the actual number, which is the number of advanced civilizations in the Milky Way galaxy. But the problem with this equation is, although Drake has given this equation, this depends upon the length of the signal dispatch, which means the signal is on for just a small second or a year maybe, we may miss the signal. right? It may not reach us, or we may miss it. So it also depends upon L. And the last four terms of this equation are unknown to us. We cannot find this yet. So this equation, although it is there, we can't really find the number n because the four terms are not known to us. And then when we talk about Fermi paradox, why have alien life not contacted us? Why have they not reached us? Or why haven't we detected them? We talk about the term called the great filter. The great filter is basically a point in the lifetime of a species which may prevent them from proceeding further. In our case, as we have observed our life on Earth, global warming may be a great filter for humans, that global warming someday may go out of hand and kill all human beings, the species. Technological takeover, that is like from the movie Matrix, where technology takes over all of mankind and probably lead to our end. We've got the asteroid impacts, like in case of dinosaurs, where one or a few asteroids can basically wipe out the whole species, or any other species wipe out events could be great filters. So Fermi tells us that it depends upon the timeline of the species, where the great filter is, that will let us know why are we alone. Because if the great filter has been behind us, then we as humans have gone past this great filter and probably will survive for a long time to come and have contact with aliens. Or if we humans are behind this great filter, then we may not live long enough to have this contact. But then the more important question is, the species trying to contact us, is it behind this great filter or is it ahead of us? Because if it is behind this great filter, then tomorrow we may never hear from them. The great filter may wipe them out. But if they are ahead of the great filter, then they may lead to something called the type 3 civilization, from which point they may proceed to a technology that can bring us here, or bring them here, or lead to communication between them and us. So when I talk about the type 3 civilization, I need to talk about the Kardashev scale, which talks about the type 1, type 2, type 3 civilizations. So type 1 civilization would be a civilization that has utilized the entire planet's resources. A type 1 civilization would use all the energy available to it from that home planet. We as humans are at the scale of 0.73. We have still not become type 1 civilization. Once the species has utilized its planet's energy, it may proceed further to utilize the energy from the entire solar system or its home's star, or the other planets that's near its star. So in this case, the civilization might have created Dyson sphere, which is basically an enclosing of the star to absorb all the solar energy from that star and utilize it. It also lead to the computer system that comes from a Dyson sphere. And then proceeding further, once the civilization proceeds further from the solar system, it may utilize energy from galaxy. This might be a quite far-fetched idea, but it's still possible. And then why stop at type 3? The Kardashev scale basically talks about type 3. But why stop at type 3? There may be a type 4 civilization which uses the energy, has communication, has transportation between the entire local group. So if this is true, if there is a civilization that is type 3 or type 4, even then, why have they not reached us? Maybe we are in one corner of the universe where these civilizations, type 3 and type 4, are very, very, very far away from us, but that still means they can contact us someday. But we as humans need to survive the great filter if it is ahead of us, and then try to maintain life on Earth as well as other planets, and then slowly find out if there's human life. Of course, when I talk about movies, all of us in our childhood or in our young ages, we have seen Koi Mil Gaya. We have come across the point where they press some buttons and send signal into space. Although it was quite comical in the movie, have we really done this? So that brings us to our hellos. So our hellos comes in the form of radio signals and physical information that we have sent into space in search for human life. So the first hello that we sent was the Arecibo's message. From the Arecibo radio telescope, they sent out a transmission that was sent towards the M13 cluster. That's the Hercules cluster in the Hercules constellation. And we haven't replied, we haven't received any response to it yet. But what was enclosed? What are all these colorful information that you see in this signal? So here on the top, you see some white boxes. These boxes are basically the number system. These are binary number system that goes from 0 to 9, which tells the aliens if they receive the message that we use these number systems. Once they figure out this number system, we have given out the atomic number of hydrogen, carbon, nitrogen, oxygen, and phosphorus, which is basically what makes up the DNA. Then we've also given them the information about the chemical compounds that make the DNA in green over here. And then we've also given out the estimated number of DNA nucleotides in the form of this white pixels over here. And then the blue pixels here talk about the helical structure of the DNA. The red structure here talks about the human form, how the life on Earth exists. The images here in blue, the pixels here in blue and white talk about the dimensions of an average human being. And also we have given them a little bit of information about the population on Earth during that time. This was sent in 1973 or 1976, I guess. And then the yellow pixels here talk to them about the solar system that we are in right now. You can see the big yellow set of 9 yellow pixels is the sun, followed by the various planets over here. And finally, the purple pixels talk to them about the radio transmitter with which the signal was sent. So this was one of our first hellos, and this was not replied back. The second hello that we sent was using the Pioneer plaque, which is basically a physical plaque on which we encoded information. And this, the destination to this is not yet decided. So like the Arecibo message, this was not pointed at one point in the sky. The Pioneer space probe was carrying this and it is headed out into space. And we have not received any reply for this. And the data in this is basically the hyperfine transition of neutral hydrogen that is shown in the image over here. And then we've also got the figure of a male and a female on this board. Behind them is the image of the probe that's carrying them, the Pioneer probe. Next to it, we've got the position of our solar system with respect to 14 known pulsars near to us. And then there's binary encoding of that as well in Morse code, I guess. And then we've got the solar system image and the path of Pioneer shown here as well. This was also used in the Voyager Golden Record. Since before this talk, we were talking about Carl Sagan, who was basically the source of knowledge and inspiration for most of us, especially about alien life. Carl Sagan was the one who designed this golden record, which basically is a physical disk. It's a disk record that contains information. Again, it's sent on the Voyager space probe. The destination is not fixed and we have not received any response. But what does the disk contain? It contains 55 greetings in ancient and modern languages. It contains human sounds, footsteps, laughter, and cries of various species on Earth. And you've also got the same pulsar location of the sun. You've got the hydrogen nuclear hyperfine structure of hydrogen here embedded on this disk. And on the top, we've got also a design to make a record player, because if an alien life really finds this, then they need to know how to play it. So this basically, the image here talks about how to design a record player, and it also talks about the various sections of the waveform or the audio tapes and videotapes inside this. So all of this encoded information is on this golden record. 2 of these have been sent on the 2 Voyager probes, but no replies have been given to us. Along with this, we've got other missed calls. I'm calling them missed calls because none of these messages have been replied to. So we've got the cosmic call, we've got the teenage message, we've got a message called Across the Universe, the lone signal, and much more. And we have received a signal from Earth, which is known today as the WOW signal. It's not called WOW signal because it contains the message WOW, but it's a radio signal that came to us from the Sagittarius constellation. And we've replied to the signal as well, for which there's no another reply given to us. And the data in this signal is unknown to us. The reason why we call this the WOW signal is because this signal contains the string 6EQUJ5, which denotes the amplitude function of the radio signal. Right? So the scientist who was studying this for the first time, the moment he discovered, he was so excited that he wrote the word wow on it. And that's why it's known as the wow signal. But years later, someone has unmuted the mic. Oh, fine. So years later, after discovering the wow signal, scientists realized that this is not probably an alien signal, but it has probably come from a comet that is passing by. So this is the reason for the wow. The amplitude here in the signal has reached a peak. which is given by this string here. And that's what leads to answer. So we've sent out communication. We thought we received a communication, but it was not. So we don't know yet if there's alien life. And when it comes to the Drake equation, the real equation that tells us about aliens, if they are there or not, then I told you the last 4 terms are unknown to us. We haven't found them. We cannot find them yet. So let's find these 4 terms, right? So before we find these 4 terms, how do we find these first few terms? So to do that, we will use physics, and here's the checklist to find alien life using those terms. Using those methods to find those terms. So the first would be to search for the stars that show a sign of planets. Because in the night sky, if you go out and observe, there's 4,000 stars. I just told you at the beginning of this talk that there is billions of stars. And how do we know that if this star has a planet like Earth around it? So first we need to search for this stars with planets around them. Then based on the planet's position, we can kind of estimate if life exists on it or not. And finally, we can study the spectrum of the planet and the star to find out if atmospheric and organic elements are present in this planet. So the first step is to find the stars that show a sign of a planet. So how do we do this? There are certain methods which include the parallax method, the transit method, the Doppler method, and we'll discuss them one by one. So you can see here in this video, the transit method basically talks about the planet transiting the star. And as the planet transits the star, which is it comes in front of the star, you see a dip in the brightness of the star. So I hope you saw that. We can I can even show it again. So depending upon the size of the star, there's a dip in the brightness of the star. Right? So if it is a large planet, then the dip in the brightness is very large. You can see here in the image on the left. And if the size of the planet is small, the dip is smaller, which is evident in the image on the right. So the transit method can be used to find out if a star's brightness dips and if there's a planet around it or not. But we should be aware of false positives as well, because when we look at stars and their falling brightness, they can be binary stars, like in this video here, where a smaller star transiting the bigger star will lead to a drop in its brightness. You can see it in the image here, that as the binary system orbit one another, there is a dip in the brightness. But I'm not sure if you're able to identify the difference between a planet transiting and the binary star transit here. So I'll make it clear through this graph over here. Whenever a binary star is observed, we observe 2 dips in the brightness. So here I can show you that the first, as the smaller star goes behind the larger star, we see a greater dip in the signal, the brightness. And as the smaller star transits the larger star, we see a smaller dip in the brightness. So this does not happen if there's a planet there. If it is one planet and one star, we see one dip, which is periodic in the brightness. But if it is a binary system, 2 stars, then we see 2 dips, one larger and one smaller dip, and that periodic signal repeats over time. So we can be sure about a planet being around a star using the transit method, using these methods. Again, depending upon where the planet transits the star, we can see that the variation in the dip also can be noted. The slope, there's a small slope here to this dip in the brightness that also lets us talk about, find out various properties of the planet. So it not only the transit tells us about if there's a planet or not, we need to consider a certain parameters here to identify the orientation of the plane of the orbit and so on and so forth. So you can see here that the dip in the brightness may be divided into 3 parts, which is part 1 before the transit, part 3 where the planet has entered the complete transit phase, and part 2 where the planet is almost beginning, or it can be on the other side, almost ending the transit phase. So you see there's a slope to this graph. It's not a 1 or 0 change in brightness. It's a gradual dip, right? So in signals, it may be immediate, but once we develop better devices, once the device is precise enough, we see that the dip does not happen immediately. So when the planet transits the star, this slope can tell us a lot about the planet as well. You can see here there are methods to find out using trigonometry that tell us if the star and the planet's orbital orientation is along the plane on which we are observing it from, or if we are observing it from a point of view where we are not on the plane of orbit, right? So you can see the image here. If we are observing the planet, we are observing the planet from the plane of orbit, then the planet will basically pass from the center along the diameter of the star. But if we are maybe located above or below the orbit, the planet may take a lower or a higher path. So this distance from the center of the star that we observe can lead us to various parameters of the planet. And that can tell us about the size of the planet using these formulas. We've also got the parallax method. All of us are familiar with the parallax method. So it's basically the method where we find or we look at an object from our eyes individually. So you can do this method at home. You can hold a pen and look at the pen from your right eye, and then you can look at the pen from the left eye. So when you do that, you will realize that from the right eye, the pen will appear to be at a position with respect to the background, and from the left eye, the pen will have appeared to shifted its position with respect to the background. Now we can do the same experiment using the sun and the earth, because the earth goes around the sun once every 365 days. We can take two positions at opposite sides of the sun, maybe in June and December, like we show in the image here. And then here, the June may be our left eye position, and the position in December may be our right eye position. And then when we observe a given star at these two positions, then you can see that the star's position with respect to the background star may vary. So in June, we may see that the star is located here away from these two stars. And in December, we may see that the star has shifted position close to these two stars. So parallax methods tell us how to find the distance to a given star using trigonometry. So you can see here, because the Earth is located at 1 astronomical unit from the sun, we can use this formula here, that distance can be found out by 1 astronomical unit divided by the angle or the parallax angle and its tangent function. So once we use the parallax method, we can find out the distance to a star. The next thing we can do is to look at the star and its color. From Planck's black body radiation, whenever we know that something is emitting some color, then we know that it is emitting at certain temperature. So based on the color of the star, we can identify what is the temperature of the star. Why is this important? I'll come to it later. But here what matters is we just observe the star and we know the temperature with which it is glowing with. So here are the various color spectrum of a star, and below them are the various temperature scales in Kelvin. So once we find the temperature of the star, we can use another formula which is known as the mass-luminosity relationship. So luminosity here basically is the brightness. And once we know a star's brightness, we can use the sun's brightness and the sun's mass to find out what is the mass of that star. This sounds very fascinating, because on Earth we are used to measuring things for mass. We are used to measuring measuring mass using Newton's laws. We need gravitational equations to measure mass. But here we have found out with various observations over decades that the brightness of the star also can be used to determine the mass of the star. So just by looking at the star and its brightness, we can identify the mass of the star, and this will play a very important role in finding out about the planet that is orbiting the star. You can see that whenever a star orbits a planet, whenever a planet orbits the star, Newton's law of gravitation says that not only is the planet being pulled by the star is being pulled by the planet as well. Not only did the apple fall onto the ground from the tree, apple pulled the earth towards it. So whenever there's a planetary system orbiting around a star, they tug onto the star and shift the star's position such that the entire system will orbit some point called the barycenter. So I can show it again to you. Here, the star is orbiting a smaller circle, and at the center of the circle here, at this point, is the barycenter, where the entire system is orbiting. This causes the star to move away from us and closer to us. So you can see that as the star is moving close to us, the frequency denoted below turned blue, and as the star is going away from us, the frequency here turns red, right? So in terms of frequency purely, I can say the frequency increases as the star approaches to us, and the frequency of the light from the star decreases as the star moves away from us. And this is known as the Doppler shift. So why do I need frequency? Whenever I'm doing any observations in astronomy, I'm going to use the frequency because there is a spectrum to every star. Every star that emits light will technically give out a continuous spectrum. The spectrum observed from the sun is supposed to have all wavelengths in it. So it will contain the entire visible spectrum. So you can see all the colors from the sun. But whenever a star is rich in hydrogen, is emitting some light, then it will show specific bands, which is known as the emission bands. And these specific bands have specific wavelengths given to, related to every single element. For example, you see here in the second image, we've got the emission spectrum from hydrogen. Hydrogen spectrum emits 4 visible wavelengths, right? One around 650 nanometers, that's close to red, and 3 variants of blue. And whenever we observe an emission spectrum giving out only these 4 colors, then we know that it is coming out probably from a hydrogen gas emitting light. Similarly, we've got absorption spectrum. That is, whenever hydrogen is in between the light source and our observation, hydrogen is going to emit these wavelengths, and this is going to create dark bands known as absorption bands. And once we figure out these wavelengths, then we know that hydrogen is present. In fact, what we see is not the wavelength, right? Because of Doppler shift, I told you, there may be a shift in this. What we see is the distance between these wavelengths that tell us about the spectrum and what is the element that is emitting or absorbing the light that we're observing. So what I'm trying to show you here is, as the planet tugs on to the star is moving, and as the star moves away from us and closer to us, the Doppler shift tells us that the light from the star will have a blue shift or a red shift. Now, the image I showed you earlier where the light turned blue or turned red is not quite accurate, but what we observe is these spectrum or these absorption bands that shift in position. You can see here, as the star is slightly moving because of the planet, the absorption bands will slowly shift. Show them again. Yeah, you can see them shift. So whenever these bands shift towards the red side, we know that it is red shift, or the star is moving away from us. And whenever these bands shift toward the blue side, we know that the star is moving closer to us. So you can see here, the bigger the orbit, the slower the shift. You can see the shift happening over here. So based on this shift, we can basically figure out the velocity of the star. So I told you, using the using the brightness and the luminosity, we can figure out the mass of the star. And then just now I showed you how the spectrum and the absorption lines of the star can tell us about the velocity of the star, if it is closer to or moving closer to us or moving away from us. And we can measure the shift in the spectrum to identify the velocity of the star. And once we know the mass of the star and the velocity of the star, we know the momentum of the star. And once we know the momentum of the star, using law of conservation of momentum, we can basically find the mass of the planet. How do we find the mass of the planet? For this, we need to know the velocity of the planet, which can be found out from the orbital radius, which I discussed in a while. And we need to know the mass of the planet, which can be identified from the brightness. We can also find the velocity of the star from the Doppler shift. So we know the 3 terms. Once we know the 3 terms over here, we can find the 4th term, which is the velocity of the planet. And we can also find the period of orbit of the star from, of the planet from the transit method as well, based on the repeating signals. So we've collected so much data about the planet, if there is a planet around a star or not, right? So the next thing to do is to find out if a planet is in a position where life exists. This is very important, because if an alien life has detected a Jupiter around the sun, then they can't be sure that there is life on in our solar system, because Jupiter is not a planet where life exists. So in a similar manner, if we detect a planet where life may not exist, it may not be useful information to us. So we need to find out planets using the earlier methods, and using further methods, we need to confirm that life exists on these planets. For this, we will use Kepler's third law to find the orbital radius, which is also used in the law of conservation of momentum there to find out the velocity of the planet in the earlier slide that I showed you. But using Kepler's law, we can find out the orbital radius of the planet. And why is this important is because once we find the orbital radius of the planet, we can find out if the planet lies in the Goldilocks zone. The Goldilocks zone is basically the just right region around any given star where life can exist. If a planet is in an orbit that is smaller than the Goldilocks zone orbit, then it may be too hot, like in case of Mercury and Venus. Or if a planet is too much away from the Goldilocks zone orbit, then it may be too cold, like in case of Uranus and Neptune. So even if Uranus and Neptune were rock-like planets like the Earth, it would have been too cold for life to exist there. In our solar system, only Earth and Mars lie in the Goldilocks zone. So we need to be sure that the star has a Goldilocks zone in which there is a planet existing for us to confirm that that exoplanet is useful to us. So you can see that in this image, various stars, depending on their size, have basically a larger or a smaller Goldilocks zone. So this becomes an important parameter for us to discover if a planet is important to us or not. I can in this image, what I've shown you here is G-type star, which is like a sun, which has a bigger Goldilocks zone. So more probability of finding life in such stellar systems. Whereas a smaller planet like a K-type dwarf, right? Such planets, such stars will have smaller Goldilocks zones, so lower probability of finding exoplanets with life. And red dwarfs, which is the M-type shown here, have very small Goldilocks zones. So finding life around such stars is practically impossible. So we need to know these parameters to know what stars to look for planets around. Once we know that a large star has a larger Goldilocks zone, we can focus our observations there to find more probabilities of life containing planets. So once we have figured out various stars that have planets around them using the transit method and various other methods, we have also figured out the orbital radius of the planet and figured out if the planet is in the Goldilocks zone or not, if it may sustain life or not. We need to look out for certain parameters or identify the atmospheric and organic elements, because the position of the planet is not what decides if life exists or not. We also need to find out if there is basically elements that support life on that planet or not. And how do we do this? We basically look at the composition of the planet. So like I've mentioned about the emission and absorption spectrum for various elements, I've shown here to you the absorption spectrum of sodium, mercury, and lithium. Every single set of lines, I won't say lines, set of lines, the combination of these lines would tell us what element lies in the atmosphere or in that light emitting object. So when I'm looking at a planet, of course, the planet is not going to give me any light. And when I'm looking at a planet using the transit method, what is actually happening is the planet is blocking the light from the star. So I'm not going to get any light from the planet in a direct manner. But what I can observe is the light passing through the atmosphere of this planet. Like the star's light from behind the planet will graze through the atmosphere. I told you the absorption lines can be observed when a particular element or a molecule or a gas is in between the light source and our observing apparatus. So if a planet contains elements that support life, if there is an atmosphere on that planet that contains life, then as the light grazes the atmosphere of the planet and comes towards us, we can observe this. And you know that every single element and also molecules, right? So when I spoke about elements, they were in the visible region, but as we move further down the frequency lane or higher wavelengths, we can find out that every single molecule also has a signature. So once I observe the complete light coming from the star system, whenever there's a transiting planet, of course, every single observation I make is not going to give me this data, because every time the planet transits the star, the light has to come move from the atmosphere of the planet and reach us. And over a long period of time, as we make more and more observations, we get more and more data that tells us about these signatures, which helps us detect a particular element in these planets. So you can see here, when the wavelength is about 14.5 micrometers, whenever there's a band, absorption band in this region, there's a emission band in this region, because we're talking about brightness over here, we see hydrogen, water can be assumed. So similarly, even in the absorption band, when we see a dip in the brightness of this 14.5 microns, we can safely assume that there is probably water on that planet. So similarly, there are other signatures as well that tell us about the atmospheric composition of these planets that we come across. So like on Earth, we can detect easily, if there's an alien life that's detecting the composition of the Earth, they can easily detect nitrogen, oxygen, which is present in our atmosphere. Methane is also present in our atmosphere now, so we can observe that as well. So similarly, we can observe this for other planets as well. And once we find out that a planet has oxygen in its environment, or maybe water in its environment, then we can be sure that human-like life may exist. So these are methods where we can identify if an exoplanet is going to be useful to us or not. So how do we find these things? What are the various devices or apparatus that are used to find all the data that I've just mentioned to you? Of course, observatories on Earth help us identify these things, but whenever we talk about observatory, they're on Earth. And you know that atmosphere causes light to twinkle, stars to twinkle, and also atmosphere causes a change in brightness. The change in basically variable brightness that is caused by the atmosphere can give us less amount of data about any given star or its planet or what. But once we have an observing apparatus in space, like the Kepler space probe or the transiting exoplanet survey satellite, the TESS we call it. So whenever we have a space probe, the atmosphere is no more a problem. And if you position these space probes at a particular point in space around the Earth, such that the sun's light is not going to obstruct their view, then we can identify more and more exoplanets easily. So using these space probes, so far we have identified, using the Hubble space probe, using the ground-based space observatories, using Kepler, using TESS, and our mathematical calculations, we have found out that the first three terms of the Drake's equation are 7 close to 1, that's 9.8, and 0.4. So the 7, the first part of the equation, tells us about a very high probability, which is closer to the first part of the question of the Fermi's paradox. If there's so much planets, so many stars, so many galaxies in the universe, then of course there's life out there in large numbers. But then you can easily see that the second term reduces that probability to you multiply it by 0.98, so it is reduced by 7, and the third term reduces it by 40% further still. And in the future, when we have James Webb Space Telescope which is going to launch in a few months, and then we have the New World Space Telescope that is being planned by NASA, which may be sent out in a decade or so, we'll have more and more data about the remaining terms in the Drake's equation. And once we've got all these data, we've also got, of course, we've got the extremely large telescope and the 30-meter telescope, which will help us identify the remaining parameters of the Drake's equation. So once we know what lies in the future, let's focus a little on the present right now. So given Kepler space probe has been studying all the various star systems for almost a decade now, let's see what it has found out. You can see in this graph very clearly that from 2009, you can see that the number of exoplanets that we have discovered is very large. And especially on 26th February 2014, Kepler made an announcement that led to almost 700 exoplanet discoveries, more than 700 exoplanet discoveries. It confirmed those discoveries. So the amount of exoplanets we have discovered is very, very, very large. Among these exoplanets that we have discovered, many of them are hot Jupiters. So they're like Jupiter, which is basically gaseous. We've got cold gas giants like Uranus and Neptune. We've got ocean worlds and ice giants as well. So there are planets, exoplanets with oceans on them. There's exoplanets with ice in them. There are rocky planets like Mars, for example. There may be planets like Mars in other star systems that we have discussed. You can see there's a lot of white spots behind this yellow region here. We have also found lava worlds where the planet may be in its primitive form. And the plot you can see here very easy, clearly, that is plotted on the size versus the orbital period. Right? And this is the data in terms of number. We've discovered Earth-size planets that are 955 in number, and this is the data from 250. So there's much more data there. And there's super Earth-sized planets, which is in the Goldilocks zone, bigger Earth-like planets. We've got Neptune-sized planets that are thousands in numbers, Jupiter, and much larger planets. And among this, we have found out there's a lot of planets that lie in the habitable zone. We've got Kepler 1638b, Kepler 1410b, and so on and so forth, that lie in the habitable zone. In fact, these are the various planets that we have discovered that lie in the Goldilocks zone of their parent star. Right? So there's so many planets for us to explore, right? So from among all these data, this is just a stats of all the data we have got. And as of 1st November 2021, we've confirmed 4,864 planets, right? Of which 3,595 are planetary systems, and 803 systems have more than one planet. 61 are habitable, and we've still got 2,366 potential exoplanets that are yet to be confirmed from Kepler's first mission. And Kepler was upgraded into a second mission in which we have got 889 potential exoplanets. And after Kepler, we have got 1,385 transiting exoplanets from the TESS space. So we have got a lot of exoplanets that we have discovered, and there's a lot of possibility of alien life out there. Among all the discoveries we've made for exoplanets, we have to talk about the TRAPPIST-1 system, because the TRAPPIST-1 system is that system where we've discovered almost 7 exoplanets, in which 3 of these planets are in the Goldilocks zone. So imagine if life exists on one of these planets, like E, F, and G denoted here, they may be able to move between E and F to G. So interplanetary travel may be possible in the TRAPPIST system if there is life on those planets. So these are the sizes of the planets and their parameters with respect to the our solar system planets, right? So TRAPPIST-1 seems to be a very promising system. And when I'm talking about life outside our solar system, I also have to talk about the life that we have estimated in our solar system. Right? So on Mercury, the MESSENGER spacecraft found evidence of water ice, right? And it gave us an estimation that microorganisms may have existed, but it's too close to the sun, so we don't find any life there yet. About a year or two ago, we came across the news that Venus may have life, right? MIT scientists discovered that phosphine was in the Venus's atmosphere, and the amount of phosphine discovered was not common to abiotic life, which means the amount of phosphine discovered in Venus's atmosphere could be explained easily if there was life on Venus's atmosphere. But again, we have not found any visible trace of life on Venus. On Moon, we have discovered liquid water's presence from various NASA and ISRO probes. Using the Chandrayaan probe, we have discovered this. On Mars, we have discovered methane and formaldehyde, but life signatures are still being searched by the various rovers on Mars. Europa, the planet or the moon of Jupiter, it has got an icy surface, and scientists speculate that there is a possible water under this icy surface, and that water may contain microorganisms. And Titan is basically Saturn's moon, and it has got water bodies. I mean, I wouldn't call it water bodies. It's got rivers, lakes, and carbon compounds that are like water bodies. And we've also got Enceladus, which is Saturn's moon, which may be a possible habitat due to the presence of carbon on the moon. So even in our solar system, there's possibility of life, but we have not yet detected so far. So among all of these discoveries, among all of these statistics, there is also a possibility of rogue planets containing microorganisms which are not discussed here. What have we found out is virtually nothing. We haven't found out any life forms yet, and Fermi's paradox still holds good. And when we look out for life outside our solar system, we come across these various codes given, and one of the codes that stands out is the code by Stephen Hawking, which says that, which is basically a pessimistic view of this discovery, that says that alien life, or inviting alien life, or sending out messages to alien life, would lead to a disaster. It may be like Columbus, who landed in North America. When he landed in North America, the indigenous population there drastically fell down. Right. So whenever an alien visits us, Stephen Hawking warned us that if we keep sending out signals to them, it may tell us where we are, and once they reach here, it may not be good for us. But just last week, around last Monday, I was listening to this podcast by Naval Ravikant, which is basically a podcast about various aspects of life. And Naval Ravikant is not a scientist; he's basically an angel investor in the Silicon Valley. But as he was discussing in this podcast, it looked like a very optimistic view of alien life to me, where he said that if alien life really exists, if aliens do exist, that can travel light years and can reach us, then they are probably the type 3, type 4 civilizations that have utilized the entire resource system of their planet, their stars, and possibly their galaxies as well. In which case, they don't need to reach here in search of land, in search of resources, or in search of slaves like Columbus did. They will reach here only for knowledge. In which case, aliens would reach us in curiosity, and it may not be, after all, negative when an alien species discovers our planet, or when we discover their planet and approach them. So with this, I guess I've covered almost all topics or all aspects of exoplanet discovery purely in terms of physics. So if there's any questions, people can ask. Thank you.
Thank you, Atul. What Navalkant Keshava said regarding the curiosity, you have in your talk, you have made the lot of curious questions regarding the existence of exoplanets and then the alien life. Now it is open for the discussion. Just those who want to make the interaction or ask the questions, you can make your speaker on and you can speak with the speaker, Atul Bhat.
Sir, here I got a question.
Yes, sir.
This you said that the when the planet moves around the sun or the star, and we can know that there is a dip in the light.
Yes.
Okay. Now, if there are, in case there are 2 or 3 planets which are moving around in the same at the same place, with not much of a difference back to back, then how do we infer there?
Okay, so let me see if I've got the question right. So if there are multiple planets around a star, we will see the dip happening around the star. And if they're back to back repeating, then how do we identify if it is one exoplanet or multiple? Is that right?
Yeah. Yes.
Okay, so whenever there's a planet orbiting the star, of course, they'll be orbiting at various distances. So from basic law of gravitation and Newton's equations, we can find out that their velocity of orbit around the star varies based on this distance. So if a star is having a planet that is orbiting around it, then it is at a fixed distance. So if there are multiple planets around the star, then each of these planets will go around the star at various periods. So all we need to do is look at the dip in the brightness, and we need to look out for period of orbit. Of course, what you've mentioned has been detected. Like I told you, the TRAPPIST system. We just need to see the dip and the periodicity of these dips, and make sure that these dips, like I told you, in case of binary stars, there's 2 dips. And we see that once we have this dip, it's not the confirmation that it is a planet. It can be a binary star. And once we see that dip, it may not be conclusive evidence that it is a planet. So there are multiple methods that I've mentioned. So we see that we see the transit method, and then of course the Doppler shift method tells us this, because just to give you an example, in our solar system, Jupiter causes the sun to orbit around a point, which for us lies inside the sun itself, inside the sun's sphere itself. Jupiter causes the sun also to wobble. And similarly, we have Earth causing this wobble. We have got Saturn causing this wobble. So if there's a multiple planet system orbiting around a star, then we need to calculate if the Doppler shift will account for this barycenter orbits, right? So if there are multiple planets around the star, we just observe the Doppler shift, and then we try to assume, okay, there is 5 planets around this star, and we calculate the movement of the star. We calculate the Doppler shift of the star, and then that will help us to confirm how many planets are there around the star.
Okay, and if there are more than 2 stars, then what is the...
That's what, sir. Like if there are 2 or 3 or many number of stars, every single star will cause a shift in the star's position. And we measure this shift using Doppler shift in the wavelength. So if there's only one planet, we see this shift happening fixed.
What I asked is, if there are 2 or more, like 3 stars moving around each other.
Oh, that's very nice. One planet orbiting around 3 or 4 stars.
No. The binary, as you said, binary means 2
Yes.
stars. If
Yes.
there are 3 stars rotating around each other, or 4 stars, something, has there been anything found like that?
Yeah. We have found multiple star systems, and we are more known to binary systems. I can't recollect any 3-star systems that has come across my studies, but it's possible. There can be 3 stars that orbit, but then the problem with this 3-star system, I mean, it's possible in terms of physics, but then it's a very big mathematical problem, because it becomes a 3-body problem, and it is very hard for us to put 3 objects in motion in orbit around one another. It's a very big maths problem. 3-body systems are very chaotic. So a slight change, very slight change in the initial conditions of one star will lead to the entire system going out of the whole, the configuration, and we'll have chaos. In fact, I would like to suggest this to you. There's this website called Minute Labs, right? So there's this website called minutelabs.io, or any other orbital simulation software. So I do this very often, that you go to such simulation softwares, and on this softwares, they'll let us create multiple orbits of various bodies. So they'll give out a sphere, and we can specify the sphere's mass, we can specify the sphere's velocity, and so on. And then we press play, and we can see what the orbit of the system is. So it's very easy to put 2 bodies in orbit. It's very easy to put one big object like a star and one small planet around it. But the moment you put 3 objects together, it becomes very chaotic. And within 1 or 2 orbit, the whole system just goes around, and the 3rd star probably completes only 1 or 2 orbit, and it just goes away. So you can try this yourself, but it's basically a 3-body problem. But it's not impossible.
What is you said, minutelabs.io?
Yeah, minutelabs.io. Let me just check it.
And another, what you said, one more?
Yeah, it's the same thing. Minute Labs, minutelabs.io. This is a website. So on that, you'll find many physics experiments, and I'll just post it in the chat. That'll be easy for you, I guess. So minutelabs.io. So if you go to this website, you'll find the orbital simulator, and using this you can try to simulate 3 stars system. But I so far have not been able to do this. So if you do, please do share it with us.
Yeah, definitely. Sir, and you said that if 2 stars are there and 1 planet is rotating around, then what is the...
For us, so far, when we observe it from Earth, to us, it observe. I mean, when we look at all the stars in the night sky, most of them are 2 or 3 star systems. I mean, 2 star systems. So if you observe through a telescope, then we will see them resolved into 2 stars. Now, if a planet is orbiting 2 stars as a whole, then I think we'll get the data. I mean, I've not studied a proper data like this, but I'm just speculating at this point that we would have to observe such a system where the brightness of both the stars will dip periodically. And if it is a 2 star system, again, the distance between these 2 stars will still be 1 light year or more than that. So it's not going to be very close right next to each other. So there may be a planet between these 2 stars. So it's a lot of possibilities. And I have not personally studied any of these data for these stars yet.
Okay.
Okay, I welcome the other listeners also to make the interaction with Atul. And this interaction between Rajpal Singh and Atul Bhat has a lot of ideas we got. Atul, whether this, what we have the exoplanets discovered, whether all these stars belong to our galaxy, or is there any other galaxies?
Yes. So far, whatever we have discovered as, I mean, all the planets that I've mentioned here are basically inside our solar system. We are still trying to find out basically, I mean, it would be very hard to observe transit of stars in other galaxies, given that they're so far away from us. All the exoplanets that I've mentioned are basically from our solar system, I mean, our galaxy.
Okay.
Sir, this James Webb,
Yeah.
Is it for only this our exoplanets or even for other purposes?
No. When we are launching James Webb, we are basically we just know that it's going to observe things in the greater wavelength regions like infrared and higher wavelength regions, not microwave and so on. It's the infrared and the red region of the visible spectrum. So we talk about exoplanets in terms of James Webb because, as I told you, when we are looking for signatures of molecules, it was the wavelength of these molecules that we see, the absorption bands, would lie in the microns band. So that is in the infrared region. So visible light will not give us this data about the atmospheric composition. But James Webb is out there to search for many more things. It's a very promising space probe. But since you've asked this question, the TESS, the TESS space probe that I mentioned, that is specifically for exoplanets. Kepler is specifically for exoplanets. Because they observe transits, they observe the Doppler shift. So we know all these exoplanets because of these space probes only. But because James Webb can observe infrared region, it sounds like a very promising telescope to us that will give out very clear details of the atmospheric composition of various exoplanets that we have already discovered and we are yet to discover.
I think the James Webb will be going to launch in the next month, though.
Yes, sir. It was supposed to be launched a few months ago, but then because of COVID, it's been postponed, and I hope it launches soon.
We're going to replace the Hubble telescope.
Yes,
most probably.
Yes.
It will be like better than a Hubble telescope, or it will be something different. I mean,
it would be different. I wouldn't say it would be better. It would be different because the wavelength that we observe using the James Webb telescope is not the same as Hubble's telescope. Hubble has been there to observe infrared, ultraviolet, and visible regions, but the James Webb will expand that wavelength spectrum into the infrared by a greater amount. So we'll be able to see further back into the universe compared to Hubble, because I've told you about the Doppler shift. As we look at objects farther in space, they will have redshifted more. So all the data that they give out to us, all the electromagnetic radiation that comes to us from farther objects, have redshifted. So we may not be able to detect them using the Hubble telescope. So James Webb is promising because of this wavelength.
Okay.
Okay, if there are no questions, it's the time to thank Atul Bhat. It's a beautiful lecture you have given. How the basic physics can be applied to see and to discover the planetary system around the stars using the its spectrum, Doppler shift, and so on. And also the Drake's equation, possibility of the number of planets, and then habitable planets, and then the existence of the life in the universe, and the probability of the presence of the alien life in the universe. And actually, this is the frontier area of the astrophysics, the search of the exoplanet, and then the signals from the exoplanets, possibility of the presence of the alien life. And that is why in 2000, I think 2016 or 17, the Nobel Prize was awarded for the discovery of the exoplanet. That indicate how much the study is going on in this particular field. And the fascinating lecture you have given, Atul. Beautifully you have explained all the things, and fantastic lecture you have given. And on behalf of the organizers and all the listeners, I have to give a big clap for the beautiful presentation. Thank you.